Uh, Hi everyone. My name is Luigi Manfretti. I am I'm faculty at RPI, of course. So I wanna try to stick to the 7 minutes. My area of work is in cyber physical power and energy systems. I work in electrical power and energy systems for utilities and for transportation. So most people would think about this like, okay, your grandma's electrical utility, but beyond the wall plug, these electrical power and energy systems are really part of the next electrical revolution. 125 years ago, we went from steam to electrical, and now we're going through that transition between common fuels to electrical. So the future is indeed electrical, and America is leadership is making this not just a nice idea that works in theory and maybe even you can for a lot of cost do it, but is making it viable economically, and that's the case of Tesla. And why I say this is the future, as you can see, these are all design concepts of electrified barrages, trucks, planes, drones. And basically, these are all power and energy systems, and they are cyber physical. They need to communicate with the external world. They need sensors, and they need help to decision making. And since you're the local American students, we need really you to stay in the lead, and you have to go beyond your imagination. So here are some design concepts also from America's industrial military companies. This is, for example, a laser weaponized ships, planes, and trucks. And all of these require high amount of electrical energy, as I explained to you. So the majority of my research is working on how to enable cyber physical systems, such as the trucks, the planes, and power grids, with network data, distributed computation, and learning. So I do a lot of work on real-time simulation, so you can run models, connect them to equipment, and harvest their data to produce real-time analytics, for example. So I work with sensors also, and of course, we're working on how to leverage all the data from measurements, either from the field or for real-time models, together with simulation models so that we can do better predictions. For example, build recommender systems for enhanced decision-making. So my research is fairly more applied than inspired, let's say. We do a lot of development of algorithms, we implement them and we test them. And the focus of these applications is on real-time monitoring, stability and control, and security, with the goal of having prescriptive analytics and also decision-making support. Some of the core science that I apply in my work is system identification, machine learning, and network science. My background is as a core electrical power, but I have expanded into these areas. I have given you a slide. So these are all my, this is my team right now. You can feel free to contact any of them. In my website, there is links to their LinkedIn for the majority. And if you are interested in working with me, you can talk to them. So this is one of the projects that or the efforts that I'm working in right now. It's NASA University Leadership Initiative Center for Cryogenic High Efficiency Electrical Technologies for Aircraft. So basically, we want to develop an entirely new concept for fully electrified aircraft, which is both powered from and cooled by liquefied hydrogen. Basically, everything in green that is going to be able to make this plane fly is an electrical power grid that needs to be sensed and controlled. And the fuel supply is fuel cells and batteries that we have to coordinate also. So, sorry, the energy conversion is fuel cells. So this is one example of research that we're doing right now. The other that just got approved, I work on power and energy systems. This is an example of integrating the electrical power with district heating, so thermal power. And basically in this project, we're trying to develop methods for optimal co-design of thermoelectrical networks with controls that can interact with the grid efficiently. So we are working on how to, if you imagine this is an entire district, as a city, for example, how do we can derive models for each of the buildings in the electrical and the thermal domain that can be then assembled together as two networks. One is electrical network, the other one is a thermal fluidic network, and how we can simulate them together in order to optimize their design, and then how to optimally control them. So this is a new project. I am looking for students for this. And finally, a lot of the work that we do is we have a lab where we actually test all of this stuff. And the basic approach that we use is that because cyber-physical systems is the place where physics meets the rules of the algorithms and the cyber world, we are using digital twins for the system that we want to control, that we want to optimize. So those digital twins are models. So we work a lot on modeling, and we deploy those models in a simulation environment that can be connected into new controls or protections or IT. This is our big setup. This is for large-scale networks. And you can see here, we deploy a model, and then you can see here the real-time data at the millisecond level being streamed from the simulations to be used for controls. Sorry about that. This is another example of our working aircraft. Here we have a gyroscopic testbed of a drone, and we have the virtual reality testbed that we're developing for the same system. So this here is the physical system, and here we have the virtual system. So we also work on how humans interact with these models for decision making, as you can see in the slides. And finally, this is our other test bench that allows us for testing control systems of renewable energy sources. So over here, the red box, that's a control system of an inverter of a large, that can be used in large solar plants. This over here on the top is another two controllers for batteries. And at the bottom, we have a real-time simulator for microgrids. So here in this test bench, we're setting this up to test how renewable energy can power microgrids. That can be just in remote locations, like in rural areas, but also in ships. So I just wanted you to see one of our recent results. Here we use both.
Luigi, you're almost running out of time, so maybe you want to wrap up. I mean, sorry about that, but I am also the timekeeper, so I'm going to let people know. Yeah, so maybe another 30 seconds to wrap up.
All right. So this is one example of how we combine both measurements and models and machine learning. So here we have measurements that we take and we use to create machine learning models, or we do it with models. And our goal is to predict failures in wind turbines, and we deploy this in different architectures. So here you can take an idea, take a look. I think I'm all done, and you can look at the slides. There was some discussion about innovations in teaching. This is a new course that you can take. It's unique in the entire United States. I think I'm the only one teaching this stuff. So it's in cyber-physical modeling and simulation. With that, please feel free to contact me. I'm looking for students to join my team for the aerospace and the district heating and grid area. Thank you.
Thank you, Luigi.